Hi. Okay, so in this video, I am going to work through the problem we started at the end of class. I won't read the whole thing, but I just remind you that the problem concerned an isobestic point. An isobestic point is a point in an absorbance spectrum where the absorbance doesn't change. And when you see an isobestic point, it's strong evidence of an equilibrium. In this case, it's between a protein, X, some ligand, which we call P, and a protein ligand complex, XP. The reason these are important is because we can learn lots of important chemical information. Namely, we can learn something about the equilibrium constant and the extinction coefficient of this protein ligand complex. The math is similar to what we've done before. So we will have an expression for the absorbance, the total absorbance from the protein and the protein ligand species. And these concentrations depend sensitively on the equilibrium constant, K. So those are the two things that we can learn in this process, equilibrium constant and extinction coefficient, which are the specific values we're looking for in the problem. So away we go. I'm going to switch over to Excel and start working through this. The first thing that we need to solve for is X0, the initial concentration of protein. I remind you that this is not the protein that's described in the problem. It's the concentration of protein that exists after you mix the protein and the ligand. So I'm going to write up here just for my own notes what the initial concentration was. This is given in the problem. 8.4 E, oops, over here, 8.4 e to the minus 6. So that's the dye concentration, the ligand. The protein concentration initially is also given in the problem, 310 micromolar. This is 310 e to the minus 6. So given those concentrations, I can figure out the initial concentration of ligand and the initial concentration of protein. These are changing because you're adding in amounts of these things. And so essentially I need to do an M1V1 calculation in order to make this work. The initial concentration of ligand is given to its initial value, 8.4 e to the minus 6, times the dilution factor. Initially I have 1 milliliter of ligand solution that's given in the problem. So that's my V1, and V tot is going to be 1,000 milliliters plus whatever amount of protein I add. This happened in class. I don't know why my thing is being so finicky. There we go. So there's my formula. I can calculate this for all of the different values, and it goes down as I add more protein. This all makes sense. Similar expression for the protein. So the initial concentration was 3.1 e to the minus 4. So 310 micromolar times a dilution factor. That be V1 is whatever volume of protein I add, plus 1,000 plus. I think I shouldn't let Excel fix my formulas. That's maybe my problem. Okay, there we go. If I add no protein, the concentration is 0. That makes sense. And this number goes down. Sorry, it goes up as I add more protein. This is all looking right. Those are my initial concentrations of ligand and protein. The next thing I need to calculate is my concentration of ligand-protein complex, XP. And if I went back and looked at that expression that I had derived before, you'll see that this depends on the equilibrium constant. This is one of the quantities that I'm trying to calculate. I don't know what it is, and so it's not something that we can calculate directly in the same way. What we're going to end up doing ultimately is making a guess for what KEQ is, KEQ, and using solver to figure out what the optimized value of it is. Now, in the past, I kind of arbitrarily guessed some number for concentrations, for instance, and then adjusted it until it sort of looked right. But it turns out with these types of problems, it's helpful to be a little bit savvier about how we guess KEQ. And so let me show you that here. In order to make a guess for KEQ, we need to recognize that there's this equilibrium that exists, x plus p goes to xp. And this is my expression for the equilibrium constant, right, how I would calculate it. I have this initial set of conditions, right? So these are the initial amount of ligand and protein that exist, right? These are initial. Reminder that the amounts that are referred to here in this expression are equilibrium amounts. And when I start talking about initial and equilibrium, you might recognize that this is sounding like an ICE table. And so we can actually use an ICE table to make a really good guess for KEQ. Away we go. We need to start picking out an initial set of conditions. I could pick any set of conditions I wanted. I'll happen to pick this first one. No, I need to have some protein present in order for the equilibrium to occur, so I got to pick something other than 0. But I'll pick this first one, and if I enter in those values into my ICE chart, I'm going to say I have 8 micromolar X, 3 micromolar P, and no XP complex. These aren't precise, and that's okay. We're just making a guess for it, and Excel is going to figure out the best answer. The next column to figure out is the change. And this is perhaps not clear from the problem, right? What is the change? I don't know. I don't know if the equilibrium strongly favors the products or reactants. And so what we're going to do is guess. And I'm just going to make an arbitrary guess, right? I like 50%. It seems like a nice round number, but you could pick something different. You could, make it 90-10 favoring the products over the reactants, or 10-90, or whatever you want. But let's just start at 50%. Well, 50% of the reaction goes, and P is my limiting reagent. That means that I'm going to lose 1.5 micromolar of P. Based on the stoichiometry between X and P, I also know that I'll lose 1.5 micromolar of X, and I will gain 1.5 micromolar of XP. Plug all those things into my ICE chart, and I would predict that if it goes 50% to equilibrium, I would have something like 6.5 micromolar X, 1.5 micromolar P, and 1.5 micromolar XP at equilibrium. These are exactly the numbers I need in order to calculate KEQ, and so I can simply plug them into an expression, and I get 1.5 times 10 to the minus 5th, right? That is my estimated value for the equilibrium constant based on my guess that it goes 50% of the way to completion. I want to emphasize to you that the specific conditions that you pick, whatever the starting value might be or the extent of equilibrium, really don't matter. If you wanted to try this on your own with your own set of values, you should certainly do it. The guess only needs to be accurate within an order of magnitude. And here we don't know a priori if we're right, but at the end of the day, if our solution doesn't converge in Excel, we may have to go back in and adjust these numbers and make it all work. So our guess for the equilibrium constant is 1.5 times 10 to the minus 5th. I'm going to go back in, and I am going to write this number in here, 1.5 e to the 5th. And I now have all of the quantities that I need in order to calculate the concentration of XP. Right? This is that long formula, and I don't have it written all the way out. I'm looking at it on a sheet of paper in front of me, and so I am going to go through and type this into this equation. I'd encourage you to look at your sheet to see where this formula comes from. But here we go. Hopefully I do this right. So K times P0 plus X0 plus 1 minus, I'm going to have a big square root. So I'm going to put a bracket on this. K times P0 plus X0 plus 1. This whole quantity is squared. I have my K value inside. It looks right. Minus 4 times K squared That's this quantity times x0 times p0. This is all to the 0.5. So let me see. I got a red bracket here and I got a red bracket here. So I think that looks right. 0.5. And that's all the numerator of my expression. I'm going to divide this by 2 times k. Away we go. Let's see. Okay. Something went off. So let me see if I can track what this error is. Oh, no, that one might be right. And I know that that one's right because I don't have any p, so I can't have anything happen. So this is actually looking right. I'm going to now propagate this formula the whole way through. And I do not want my KEQ value to change as the formula propagates. So any place where I referenced the equilibrium constant, I'm going to put in the dollar signs to keep that constant. So this one, it's like this one, and this one. It's like this one, this one. All right. And now I can propagate the formula. And now I'm getting some values for concentrations of XP. It's hard to know a priori if these things are right. But if I'm looking at my initial set of conditions based on my equilibrium constant, I said that I should get about 1.5 times 10 to the minus 6. And that's what I seem to be calculating here. So this all seems to me to be working. I can now calculate what my concentration of X is. Again, this was this mass balance condition, and you should go back and look at the derivation that was in sort of the notes. But this is going to be my initial amount minus the amount of XP. Okay, I will propagate that formula. And now I have everything that I need to calculate this. Yep, I'm just looking at this. I have my concentration of X. Oh, here's the concentration of X, and here I have the concentration of XP. And so now I am going to go through and perform a calculated absorbance. Right? That calculated absorbance, I will flip back over here. Is given by this expression. It's an extinction coefficient of X times its concentration plus the extinction coefficient of PX times XP. One of the unknowns I'm solving for is this extinction coefficient of EXP, so I'm going to have to probably make a guess for what that is. But if I look at the statement of the problem, I can learn something about the extinction coefficient of compound X. The extinction coefficient of X in molar per centimeter. Initially, I'm told that when I add no protein, I have this absorbance in a 8.4 micromolar solution. So I can calculate the extinction coefficient of the ligand by taking its absorbance, 0.0264, and dividing it by its concentration, 8.4 e to the minus 6. 3143, right? To 4 sig figs, it's 3143 per molar. Recognizing that I'm going to have to make a guess for the extinction coefficient for the compound or the complex. I have no idea what this is going to be. As an initial guess, I'll just guess it's going to be the same thing as the other one. So I don't know, 3143. I don't like the way that number looks. Okay, I have everything I need, so I can calculate this value. The calculated absorbance is the concentration of X times the extinction coefficient. Sorry, no, that's right, the extinction coefficient. I want this to be constant, so I'm going to leave that the same. Plus the concentration of XP, that's this one, times the extinction coefficient of XP, that's this one. And again, I want that extinction coefficient to be constant, so I'm going to put the dollar signs in. right? This is looking pretty good at the initial set of conditions. I have no protein ligand complex, so that hasn't impacted anything. That's pretty good. If I propagate the formula, I get some numbers. They're shown here. And what I can see is that they're basically low, right? Here, they're kind of close, but when I get down towards the bottom, they're basically an order of magnitude off. And so this might work. It might be close enough to work, but what this is suggesting to me is that my guess for the extinction coefficient of the protein ligand complex is off, right? Because I want these numbers to be bigger. I'm going to increase that value, right? And that impact is the biggest when I have the most amount of protein. So I don't know. I'm just going to toss another 0 on this and we'll see what happens. Okay. If I toss another 0 on it, it's looking much better. It's getting closer. So I've calculated all my values. I have a calculated absorbance. At this point, I can go through and do the linear least squares. So that requires me to take a calc minus a measured and square it. So here is my calculated value minus the measured value, quantity squared. I propagate that formula. I'm pretty sure that this is right. Yep, it's good. I am going to take and sum all of these. So I'm going to sum them. That's my sum. And now I'm going to hop in and do my solver. So data, solver. Here we go. What's my objective cell? Well, in this one, I want this sum cell. So it's that one. I want that to be a minimum. And I am going to do it by changing those guys. All right, let the magic happen. $1.99 times 10 to the 5th, and whatever this number is, something 16,000, right? These are my optimized equilibrium constant and extinction coefficient of the unknown. Those are exactly the values I was looking for in the statement of the problem. Wrong screen, this one. So if we went back and looked, it's asking me at this very last line to use solver to figure out the extinction coefficient and the equilibrium constant. Those are the numbers I have right here. So I am all done. Hope that was helpful. I'll check in with you in class, and good luck as you work through all this.